Ever wonder why we still learn to count in our heads when we have a supercomputer in our pockets? Astra, why run on foot when I can just take a taxi?
Because a calculator is just a crutch, Alex. Mental math is about building neural connections. It's athletics for the faster you count, the faster you make decisions in the real world. Want me to show you how to cheat the system?
I'll get a big, dusty old calculator. The plastic is starting to crack and crumble. What's wrong with it?
Turning into a shining galaxy of pure data. Ready to see math like a superpower? Let's dive in.
Why do we write numbers one under the other? It feels like I'm just drawing a skyscraper of math. Who even invented this? It seems so much harder than just counting on my fingers.
You can thank ancient Indian and Arab mathematicians for that, Alex. The main secret is place values. Every number has a home, units to units, tens to tens. Without this system, we'd still be counting on stones or struggling with symbols like these. Watch what happens when we convert them. LXVI becomes 67. It's a transformation. Now, we line them up in the grid. See how the 7 and the 3 sit perfectly in the units column? By organizing numbers this way, the math actually does itself. It's like a sorting machine.
So the column is basically the world's first calculator interface?
Exactly. It allows us to handle infinite numbers with only 10 symbols, 0 through 9. Without these columns, modern science, computers, and even space travel wouldn't exist.
So next time you write a column, remember, you're using a 1,000-year-old superpower. 68 plus 27. Let me think.
Wait, don't struggle. Let's make the numbers work for us. See 68? It's so close to 70. Let's just borrow 2 from the other guy. 68 sucks in those 2 points and boom. It becomes a perfect 70. Now, 27 is down to 25. Much easier to look at, right? Now, just add 70 plus 25. Even a toddler can do that. 70 plus 20 is 90 plus 5. 95. Magic. This is called the compensation method. Round up, then subtract the difference later.
Whoa, it's like a puzzle. I'm not calculating, I'm just moving pieces.
Exactly. But subtraction? That's where most people trip. Want the secret?
Subtraction is the worst. My brain literally slows down when I see 100 minus 64.
Don't subtract it, Alex. Flip the script. Ask yourself, how much do I need to add? Think of it as a gap. How far is it from 64 to get to 100? First, just add 6. That brings you to a nice, round 70.
Now, how much more to hit 100? Just 30 more.
Add your jumps together. 30 plus 6 equals 36.
It's like a scale. You're just finding the weight that balances it out.
This trick works for everything. Buying groceries? Calculating change? It's instant.
I spent years crying over columns, and all I had to do was jump.
Exactly, but we're still counting from the right. Let's learn to read numbers like a pro. In school, they teach you to calculate from right to left, starting with the ones. But that's not how we think about it. We read from left to right. We speak from left to right. So why count backwards?
Meet the Ferrell method. It's the secret to lightning-fast mental math.
Let's try this. 345 plus 123. Seems big? Not if you break it down. Step 1. Look at the 100. 300 plus 100. That's 400. Step 2. The tens. 40 plus 20. Easy. That's 60. Step 3. The ones. 5 plus 3. 8. Now put it together. 468. 468.
Wait, this really helps me navigate the star charts faster.
Don't worry about carrying numbers. Just add the chunks as you see them. No more backwards counting. No more forgetting the carry. Just straight line speed.
Ready to try? Head to the next level and let's see how fast your brain can fly. It annoys me to take up column digits, 1000 minus 456. All these dots over zeros.
Forget it, Alex. The rule is simple. Subtract all the digits to make 9 and the very last one from 10. Imagine the zeros are like a slot machine. They roll over to reveal the secret numbers. Look at the 4. What plus 4 equals 9? It's 5. 9 minus 4 is equal to 5. Now the 5. Subtract it from 9 to get 4. 9 minus 5 is equal to 4. And the last digits? Subtract that 1 from 10. 10 minus 6 is equal to 4. Put it together. Total 544. No borrowing, no dots, no stress.
Wait, does this for bigger numbers? Like 10,000?
Absolutely. 9 minus 7 is 2. 9 minus 2 is 7. 9 minus 3 is 6. And 10 minus 1 is 9.
2,769. It's like a cheat code for my brain.
Just remember, all from 9, from 10. You'll never get stuck in the zeros again. Master the secret of the nines. Mathematics is just a game when you know the rules.
Oops, the calculator gave me 500 instead of 5,000. I didn't even notice until now.
It's a trap, Alex. If you stop thinking, you stop seeing the big picture. Always do a rough count first. It builds your mathematical intuition. If you add 2,100 and 3,200, the result must be more than 5,000. Your brain should flag anything else immediately. It's like a scale. On one side, the exact number. On the other, your rough guess. This isn't just math, it's a sanity check for your life. Does the answer make sense? Think of it as a guardrail on a mountain road. It keeps you from falling into the abyss of errors.
I feel like I'm finally seeing the matrix. The numbers aren't just symbols anymore.
You've mastered the base. But are you ready to see how I really think? To the abyss.
Okay, that's enough tricks for the grocery store. I feel like a math wizard already. But what about you, Astra? You handle millions of operations every second. Is it just columns for you too?
Astra's expression changes. Her eyes begin to glow with an intense, steady white light. Oh no, Alex. In my world, there are no numbers, no columns, no paper. There are only electrical impulses, logic gates, and the speed of light. Do you want to look under the hood? To see how the magic actually happens? The camera begins to zoom in faster and faster, directly into Astra's glowing eye. Suddenly, the world of stars and galaxies is replaced by an infinite space of pure code.
Whoa, it's beautiful. But it's so cold, and so fast.
Welcome to the core. Forget everything you knew about 10. Here, only 2 matter. In my world, Alex, 1 plus 1 isn't 2. It's 1, 0. We speak in binary. We use only 2 states. Either there is current or there is no current. 1 or 0.
So the whole mathematics of the universe is just a bunch of switches for you?
Exactly. Let's look at the translation. Your number 9? For me, it's 1001. Instead of tens, we count in powers of 2. 2, 4, 8, 16. Watch the grid. It pulsates in time with the electrical current. I can convert any number in a nanosecond. It's just light speed logic. This isn't just theory, Alex. It's how the hardware under your fingertips actually works.
So, if I want to say 3, I just flip 2 switches? 1, 1?
You've got the code. Now, let's see the machines that do the adding. Meet the half adder. To add 2 bits together, I don't use a brain. I use a half adder, a simple machine of logic. We start with 2 inputs, A and B. They can only be 1 or 0. First, they hit the XOR gate. This gate is picky. It only gives a 1 if the inputs are different. The XOR gate gives us the sum. 1 plus 0? The sum is 1. But what if both are 1? That's where the AND gate comes in. It only activates if both A and B are 1.
The AND gate produces the carry. It's like the one you keep in your mind when adding in columns. So, this isn't just a formula, it's a physical path for electricity?
Watch. 1 plus 1. XOR gives 0 and gives 1. Put them together. 1, 0. This is the base of all digital logic. Every game you play, every video you watch, it's all built on this.
But this only adds 2 bits. How do we add billions?
We chain them. Let's build a cascade.
The half adder is cool, but it only adds 2 tiny bits. How do you handle giant numbers?
We upgrade to a full adder. It doesn't just add A and B, it accepts a carry from the previous step. To add large numbers, we connect these adders in a long, beautiful chain, a cascade. The transfer bit runs through them like a spark traveling through a fuse. We call it ripple carry.
So if I add 1,000,000 and 1,000,000, that spark has to travel through every single adder?
Exactly, but in a modern CPU, that spark travels at nearly the speed of light. It's over before you blink. While you are still thinking of the first digit, I've already finished the whole cascade.
It's like a giant digital domino effect. 1 changes everything down the line.
This architecture is the heart of every calculator and supercomputer on Earth. But wait, if you only know how to add, how do you subtract? Astra, welcome to the mirror world.
Wait a second, Astra. If the hardware only knows how to add, how do we subtract? Where is the minus button?
That's the beauty of it, Alec. I don't subtract, I just add a very special kind of number. First, we flip every bit. Every 1 becomes a 0, and every 0 becomes a 1. It's called inversion. Then, we add 1 to the result. This creates what we call 2's complement, a digital negative.
So if I add this weird number to a positive 1, it actually subtracts?
Exactly. Watch. The extra bit at the end just falls off. It's called an overflow.
The result left behind is 0010, which is exactly 2.
This is how I stay fast. I don't need 2 different machines for math. I just need one, the adder.
It's a mirror world. Everything has a shadow that makes the math balance out.
It's elegant, yes. But if the number gets too big for its shadow, things explode.
What happens if the number just gets too big? Is there a limit to your world?
Every computer has a bit grid. 8-bit, 32-bit, 64-bit. It's like a bucket that can only hold so much water. When you add 1 too many, the number spills over. It resets to 0 or turns into a total mess. This isn't just a glitch name. In '96, it caused a real-world catastrophe. The Ariane 5 rocket exploded because it tried to cram a 64-bit number into a 16-bit cell.
Wait, so a math error can actually blow up a rocket? Exactly. The guidance system just quit.
$500 million gone in 40 seconds. All because of one overflow error.
How do you prevent that now? Do you just use bigger buckets?
We use checks and balances. If the bucket is full, the system triggers an emergency stop. Mathematics is much more dangerous than you thought. Wait until you see how we handle fractions. It gets weird.
Astra, if binary is just whole switches, how do you handle something tiny, like 0.001?
We don't store them as long strings. We use floating point, basically scientific notation for computers. Every floating number has 3 parts: the sign, the exponent, and the mantissa.
Like a digital address.
The first bit is the sign, 0 for positive, 1 for negative. It's the traffic light of math. The exponent tells us where the decimal point floats. It can make the number massive or microscopic. The mantissa stores the actual digits. The more bits we give it, the more precise we are.
But some numbers, like pi, never end. How do you fit infinity into a bucket?
We can't. We have to round them off. And that creates tiny rounding errors, the ghosts in the machine. If these ghosts stack up, they can crash a system or move a bridge by several inches.
Who knew tiny dots were so powerful?
Ready for the final test? Let's combine it all.
Astra, I see it now. From ancient stones to binary code, it's all just one big language.
Exactly. You've upgraded your brain's operating system. You don't just calculate, you understand.
I'm ready to go back. I'll never look at a receipt or a computer the same way again.
Remember, add from the left, find the 9s, and never fear the overflow. This knowledge connects you to the engineers of the past and the AI of the future.
Math isn't a chore anymore. It's a superpower.
And what about you? Are you ready to dive into the next dimension of logic? Subscribe to join our mission. We're just getting started with the secrets of the universe.
See you in the next block.
See you in the next block.